right, is this thing on? Just a quick review of the demos. And this was the frozen block demo, which was about a really endothermic reaction, but an even easier example to think of here for endothermic is ice becoming water. Okay, this happens at 0 degrees Celsius. When ice melts, initially it stays at 0 degrees. There's no temperature change associated with the ice itself and the water itself, which is our system. However, the surroundings do undergo a temperature change. And why is that? Because ice has less energy than water. And what kind of energy is that? It's like potential energy. If you want to convert ice into water, you have to add energy to it. And that added energy is absorbed from the surroundings as heat. Okay, so the surroundings lose heat, which is why the surroundings get colder. But once the system, the ice absorbs it, it doesn't continue to be heat. It doesn't continue to be thermal energy. It's converted to a different kind of energy, which is potential energy. Okay, so it's like an energy conversion or transformation. Just like when you drop a ball and the potential energy becomes kinetic energy, you can convert one kind to another one. So you could think of it as if it was possible to add heat to a ball and to have it stay the same temperature, but to get lifted up, it's just like that. So that the heat kind of disappears in terms of thermal energy because it's converted to a different kind of energy that's not associated with a temperature change. Okay, so we would say the products have more energy than the reactants, which is why in order to make them, it needed to absorb energy. You could also say so remember that breaking bonds requires energy. So if this was a reaction, I guess we're breaking bonds in ice, breaking intermolecular forces. Breaking the bonds in the reactants requires more energy than the energy released when the bonds in the products form. So often in a chemical reaction, you have to break bonds in the reactants. Like let's think about this reaction, which is endothermic. And we know that this reaction is endothermic, hydrogen becoming water becoming hydrogen, oxygen is endothermic because the reverse reaction is quite exothermic. So this reaction must be endothermic. Okay, if you think about this reaction, in order for this reaction to occur, you have to break the bonds in the water. And then when the products form, you make a bond between the H's and you make a double bond between the oxygens. So it's like energy goes in, energy goes out. So it's like the lemonade stand. How much money went into the lemonade stand and how much money was produced, generated by the lemonade stand. So in this case, if this is an endothermic reaction, that means the energy you had to add to break all of these bonds was so great that the energy made when these bonds formed did not cancel out this energy that had to go in to break those. So there's an overall energy is required compared to the energy that's generated. Just gonna move on. Okay, so let's do a reaction pathway here. So we're gonna here's our line. We're going to draw two reaction pathways for exothermic reactions, but one is going to be really exothermic and one is going to be not very exothermic. Okay, so we're going to call this energy or potential energy if you prefer. There's lots of different ways you can describe that, but potential energy is fine for us. Okay, progress of reaction, Rxn's reaction. Okay, in an exothermic reaction, the reactants have more energy than the products. You might just be inclined to write it like that, which is not quite right because of activation energy, which we'll talk about later. So there's a little hump, and then it goes down. So let's say this is one of our reactions. How could we draw a reaction that releases very little energy? It would still be exothermic, and this doesn't really matter too much, but it would be more like this. Okay, so how exothermic it is a measure of the difference between the energy that the reactants have and the energy that the products have. So this is our large difference, and this is our little Christmas theme here, smaller difference. This amount here, just to, if in case you want to have it labeled because it bothers you that it's sitting there, this is our activation energy, and how tall it is meaningless for this discussion. More of a kinetics question. So we'll just have it there, that little bump, and then forget about it. Okay, when we're dealing with temperature and heat, which of the two do you guys feel? Do you have a guess, Mr. Prestwood?
What was the question?
Do you feel temperature or heat?
You feel heat.
You feel heat. Okay, that's exactly right. Thank you. So I'll call on you guys next time. Okay, so what you feel when your body changes temperature is because heat is going out of your body or heat is going into your body. So you're not necessarily, like for example, if Mrs. Abraham has this like metal grinder in the classroom where you can like grind a piece of metal to make it smoother or something. I don't know what its utility is. Anyways, so it lets off a bunch of sparks when it does that, and you can actually let them hit your hand because they're so small that even though they're like 5,000 degrees, each one does not have very much heat total because it's so tiny. So you can have a really hot thing that's really tiny, and because it can only transfer a tiny amount of heat to your hand, it doesn't cause you harm. And you're just feeling the heat from it potentially, but not the temperature of the object. Okay, so this is going to say you feel heat transfer. So temperatures measure of the average kinetic energy of a particle. Do you know that? Okay. So we can't really measure heat. We can only see what kind of changes happen as a result of heat transfer. So does a temperature change always involve a transfer of heat? In other words, in order to cause a temperature change, does heat have to be transferred? Yes or no?
Yes.
So, I was going to call on Sonia. That was rude. Yes, it does. Okay. Okay. Does a transfer of heat always involve a temperature change? So, in other words, Sonia, is it possible to transfer heat to something and not change its temperature? Sonia? Yes. Sorry. I phrased that weirdly. No, it does not always involve a temperature change because you could cause a phase change with heat, or you could cause a reaction to happen that would not change the temperature. All right.
Is this thing on?
Okay, the system is the reactants and the products. That's it. Literally, it's just the atoms that are reacting. Okay, so it's important to note that everything else in the entire universe, which my children call the university, is considered the surroundings. Okay? So, for example, if a reaction happens in water, like this pink, whatever this pink thing is happening, the water, what do you think the water is? The system or the surroundings? Let's say that it's like an acid and a base reacting and neutralizing each other. Is the water part of the system or is the water part of the surroundings? It's part of the surroundings. So if the water's temperature goes down because of a reaction happening inside the water, that means that the surroundings are getting colder. If a reaction happens in water, like for example, if you dissolve a salt in water and it gets colder or warmer, if the water gets colder, it is endothermic. If the water gets warmer, it is exothermic. The water, some of the water is interacting with the salt that dissolved, most of it is not. So the water is part of the surroundings. Okay. How do we measure heat? What is the international system, SI in French, unit of energy? Joules. Okay, so heat is just a form of energy. We can measure it in joules. We can measure it in kilojoules. Okay, another unit of energy is defined as the amount of heat needed to raise the temperature of 1 gram of pure water by 1 degree Celsius. That's called a calorie, which is actually related to food calories. I think food calories with a capital C is actually 1,000 little c calories, which you don't have to know that. That's a little confusing. But one thing, the Tim relationship here is that when I studied abroad in New Zealand, all the nutritional information, instead of having the calories listed in calories, it was listed in kilojoules. And my roommate, who was from Pennsylvania, didn't know what the relationship was between kilojoules and calories. And so she would eat these cookies called Tim Tams, which you can get in America now. And she would eat like an entire package in one sitting because she didn't realize that it was over 1,000 calories. Fun fact. Okay, so the specific heat capacity is kind of a tricky thing to wrap your head around, but it's really it's important and it's not that difficult once you think about it. So basically, if you think about having like a little cube of water, let's say that it's 1 cubic centimeter, so it's 1 gram, right? And let's say that it's at 1 degree Celsius. We can measure like how much much heat do you have to add to that gram of water in order to change its temperature from 1 degree to 2 degrees Celsius? The amount of heat you would have to add would be 4.18 joules. And that is called the specific heat capacity of water. Okay? So it's for other substances, like if it was something like gold or aluminum, it would be much less heat would be required to change its temperature that much. So it's basically a measure of how much heat is needed to change something's temperature. And it's measured per gram, per change in temperature that you're trying to achieve. Okay, what are some possible units of C given this equation? So C equals Q over M delta T. So C could be joules per gram degrees Celsius. It could be joules per gram Kelvin. And think about, how does a Celsius degree compare to a Kelvin degree? Which one is bigger? They're the same. So a change in temperature in Celsius is the same as the change in temperature in Kelvin. Okay. So what does it mean for a substance to have a very high specific heat capacity conceptually? How does it respond when heat is added to it? So let's say that this substance up here, instead of having a specific heat of 4.18, let's say it had a specific heat of 10. That would mean that you'd have to add 10 joules of heat to change its temperature 1 degree. So things with really high specific heat capacities are resistant to temperature changes. In other words, a significant amount of heat is required to change its temperature. Whereas something with a really low specific heat, like metal, you add a little bit of heat to it and its temperature jumps up. How are we doing here? Okay. For example, a 6 gram sample of glass gives off 12 joules of heat. So this, just by the way, it can we can talk about gaining or losing heat here for this, these kinds of calculations. If the temperature of the sample changes by 4 degrees, what's its specific heat? So we're basically saying C equals however much heat caused for 6 grams to change by 4 degrees Celsius. And we would get 0.5, 160 joules per gram degrees Celsius. Okay, these questions are going to help us conceptually understand what is happening with specific heat capacity. Okay, so you have 1 gram of gold, and it's at 10 degrees Celsius. And you have 1 gram of water, and it's at 10 degrees Celsius, okay? So if you add the same amount of heat to both, 10 joules, the question is, will they have the same temperature change? Will they have, or will one of them have a larger temperature change, which will lead to it having a higher final temperature, okay? So I want you first to take a guess. Think about it for a second, take a guess. Okay, if we add 10 joules of heat to each, which will have a higher final temperature? Will? Yeah, good. It's the gold. Okay, so the reason is gold has a lower specific heat capacity, which means that less heat is required to change its temperature, to change the temperature of 1 gram, 1 degree Celsius. I don't know exactly what gold's specific heat is, but I think it's like 0.1 joules per gram degree Celsius. So if we wanted to actually solve this out, we could say, we could use this equation just for future reference. We can call this equation MCAT. Okay, Q equals MCAT. Okay, so basically if we had 10 joules, 1 gram, specific heat of 0.1, the temperature change that would take place would be 100 degrees. That's crazy. That's a lot. Okay, conversely, for water, we can set up the same equation. Maybe I should move this one over here. Okay, for water, same equation, Q equals MCAT, same temperature, same heat, same mass, different specific heat. We'll say water's is 4, even though it's 4.14. When we do this, we get 2.5 degrees. So you can see that because water's specific heat capacity is 40 times greater than gold's, when they are exposed to the same amount of heat, the same amount of heat is transferred to them, water's temperature change will be 40 times less than gold's. So why don't you take a second to think about this one. Assume the specific heat of aluminum is 1 joule per gram degree Celsius. How much heat is required to raise the temperature of 10 grams of aluminum 10 degrees Celsius? Okay, so you can solve it out mathematically. Let's do that first. Mass is 10, specific heat is 1, change in temperature is 10, 100 joules. Okay, but it's also nice to be able to conceptualize it. Every gram, if you're going to heat it, 1 degree Celsius requires 1 joule. Okay, so if you have 10 grams and you try to raise it 1 degree Celsius, it'll require 10 joules. And if you have 10 grams and you want to raise those 10 grams 1 degree Celsius 10 times, then you have 10 times 10, 100 joules total. Okay, last question. The specific capacity of water is 4. How much heat is required to raise the temperature of 10 grams of water 10 degrees Celsius? Okay, every gram requires 4 joules to go every degree. Okay? So if we have 10 grams and we're going 10 degrees, we're going to multiply this by 10 twice. Okay, so we're going to get to 400 joules, which makes sense that it's 4 times as much as this, which makes sense because the specific heat of aluminum is 1/4 the specific heat of water.